We are going to begin our very last section. It's a very short section. Hopefully you guys can tell that by the notes. It's just a front and a back. We're going to talk about something called the dot product. So the dot product of two vectors is defined as follows. If you take a vector A and you dot it with a vector B, we read this as dot. I know it looks like a multiplication symbol. It is not. So A dot B is defined as A1 times B1. So you're going to take the x parts of the component form, multiply them together, and then add that to A2, B2. Again, I know it looks a lot like a multiplication symbol. It is not multiplication. Two vectors are orthogonal to each other, which is the same way as saying perpendicular. I'll explain why we have that other word for it in just a moment. Two vectors are orthogonal or perpendicular to each other if, when you do the dot product, the result is 0. The reason we have this word orthogonal, when I'm dealing in just a flat plane, so just like what I could draw on a piece of paper, if I have two things that form a right angle with each other, we say that they are perpendicular to each other. But when I start introducing 3 dimensions, length, width, height, so something traveling through space this way, that's not an x-axis, a y-axis, or even a z. I want to know if some vector that's heading off this way is perpendicular to some other vector. So we have this new word, orthogonal, to try to describe if I'm looking at a flat plane like this table, and I want to know if there's something that's forming a right angle with that. But for our purposes here, if you want to just use perpendicular as a synonym for orthogonal, that's perfectly appropriate. So two vectors are orthogonal, perpendicular, if and only if the dot product comes out to be 0. Two vectors being parallel. We've actually already touched on this a little bit. You don't need the dot product to determine if two vectors are parallel. Two vectors are parallel if and only if my vector A is equal to some scalar times my vector B. Let me give you an example of parallel vectors.
What does that stand for?
Just some scalar value. I'm going to let vector, I don't know, let's call it vector t be equal to 2, -10. I'm just adding some examples of parallel off to the side because we had some huge confusion about this earlier today, so I want to try to clear that up. If I have another vector, let's call it S, and it's equal to 1, -5. Could you multiply vector S, both of the parts of that vector, the 1 and the -5, could you multiply those each by something and get vector t? What would you multiply each piece by? 2. That means they're parallel. So t is equal to 2 times S. So that means these are parallel. If you can look at either one of the vectors and you're saying, ooh, if I just multiply this one, both of the parts, by 2 or by 5 or by 1/2, and I can get this other vector, then they're parallel. Remember, with vectors, location doesn't matter, but direction does. I'm going to run out of room here. So that first vector t that I wrote, there's my vector t. Vector s is right here. Do you see how they fall along the exact same path? They have the same direction. They don't have the same magnitude. They're not as long as each other, but they have the exact same direction. Those would be parallel to each other then. Because location doesn't matter. I can move them far apart from each other. They're still going the same direction. Does that help to understand what I mean by parallel there? Okay. Orthogonal would mean perpendicular, so they're heading in like 90-degree directions to each other. I want to practice with these 4. We are going to find the dot product, and then we're going to determine, are they orthogonal, parallel, or neither. All right, so when I go to find the dot product, we're going to multiply the x parts of the components together. So for u dot v, I'm going to do 3 times -5 plus, and then we multiply the y parts of the components together. -2 times 1. What's 3 times -5? -15 plus -2 times 1? -2. So u dot v would be what? -15 plus -2 gives me -17. Did we get 0?
No.
No. So that means they're not orthogonal. Not equal to 0. So not orthogonal. Go back and look at the original 2 vectors. Do you remember how when I was talking about parallel vectors over here, I said, could you multiply s by something to get t? And you guys are like, yeah. I can multiply both parts by 2 and I can get vector t. Could you do something like that over here with u and v? No. I can't multiply 3 by something and get -5 and multiply it same value here and get a +1. There's no number that does that. So they are not parallel. There is no scalar. When I say scalar, that just means it's a number. It doesn't have a direction. It's just a whole number or a fraction or a decimal. No scalar such that u is equal to my scalar times v. So not parallel. So if they're not orthogonal and not parallel, I would say what? Neither. What about number 2? I want the dot product first. So tell me the parts that we're going to multiply together.
Negative 2 and 9, negative 3, negative 6.
-2 and 9. And I'm going to add that to -3 times -6. What is -2 times 9?
Negative 18.
-18. Plus -3 times -6? Positive 18. So what is my dot product? 0. What does that mean about these two? They are orthogonal. If I dot them together and I get 0, they are orthogonal. What about number 3? What are we multiplying together here on number 3? If I want to find the dot product of u and v. We don't have to use the I, we don't have to use the j, so what are the numbers that we're going to multiply then? 2 times -5 plus -5 times -2. We're multiplying the I parts together and the j parts together. So 2 times -5? -10 plus -2 times -5. Positive 10. So my dot product would be 0. What does that mean about these two vectors? They are orthogonal.
Is that a dot or multiplication sign?
It is a dot.
What does it mean?
That's what we have up at the top. The definition of the dot product is up at the top in red.
Why couldn't they just like,
Make up a new symbol?
yeah.
I wish I knew. Math recycles symbols like nobody's business.
So it's just a dot.
It's just a dot. You know it's the dot product when the two things that have the dot in between are vectors. So if you see something that looks like multiplication, but it's in between two vectors, it's the dot product. I want you guys to do number 4, and then we'll stop there. What did you get when you dotted u and v together here? 39. Are they orthogonal?
No.
Are they parallel?
No.
No. So I would say neither here. If you're in doubt of whether or not they're parallel, you could always sketch it. When you have component form, when you have IJ form, they're telling you where that terminal point is. They're telling you the X and the Y part of the terminal point. So you could sketch it out like I did over here when we were talking about parallel. If they're going in the same direction, if they have the same slope, then they would be parallel to each other. Right? You guys can honestly get through about half of the homework just with what we've done. You can answer everything except for where it asks, what is the angle? We'll talk about how to find the angle in between the two vectors tomorrow, but anything where it's asking what is the dot product, you guys can do that part. Or are they parallel versus orthogonal versus neither? You can answer those parts as well.